Hi students, in this video we are going to discuss about strain displacement relationship matrix for CST. Okay, the CST means constant strain triangle. So before going to do that derivation, we have to understand what is plane stress and what is plane strain. Okay, plane stress means when the elastic body is very thin and there are no loads applied. That means I will show you an example. Suppose here we have one plate like this with small thickness. If this is the thickness T, okay, here in both the direction we'll be having stress, but here in this direction we don't have that stress, that is negligible, or we won't consider that stress. So we are going to consider only stresses in two directions. That is what plane stress, and that can be written as in the matrix form E by 1 minus mu square in 3 by, this is 3 by 3 matrix. Okay, 1 mu 0 mu 1 0 0 0 1 minus mu by 2. Here mu is Poisson's ratio. Okay, similarly plane strain, suppose you consider one dam. Okay, this is the dam. Okay, these are the gates. Here we have water. If the load is acting like this, here we have to consider only in upward direction as well as this forward direction. This side you can extend this dam length. Okay, in this direction strain is neglected and we are not going to consider the strain. That is what plane strain. Here this is plane stress. Okay, plane strain, the member that are not free to expand in the direction perpendicular to the applied load. That can be expressed as E by 1 plus mu into 1 minus 2 mu, 1 minus mu, mu 0, mu 1 minus mu 0, 0 0 1 minus 2 mu by 2. Again it is 3 by 3 matrix. Here mu is Poisson's ratio, that is lateral strain by longitudinal strain, and E is the Young's modulus, that is in Newton per mm square. Now if you want to consider any point, suppose delta, okay, that is the elongation, we need two coordinates, that is x comma y, and that can be written as u in the direction of u, 2 points x comma y, in the direction of v again x comma y. Here I will write the same thing with shape functions n1 0, n2 0, n3 0 0, n1 0, n2 0, n3. Why I am writing like this means this 3 belongs to u1 u, and this is v v v, u1 u2 u3 v1 v2 v3. That means here we have one matrix u1 v1 u2 v2 u3 v3. Okay, see here n1 into u1 will get n1 u1. Here it is 0 because here we have v. This is only related to u, that's why we have u after v, again u after v, again u after v, like this. So n1 0, n2 0, n3 0. Similarly the first one is u1, that's why here it is 0. The second one is v1, that's why it is n1 v1, because the second one is for v. See here u is equals to n, that is row into this column, n1 u1 n2 u2 n3 u3. Okay, similarly v n1 v1 n2 v2 n3 v3. Okay, now we have to calculate the strain in this triangular element. The strain, which is the ratio displacement to length. Ratio displacement to length can be x and y axis displacement. That can be u and v. Okay, we'll write one by one. First, the normal strain. I will write the normal strain in x direction. The strain can be written as epsilon x, that can be dou u by dou x. Here already we know u value, that is n1 u1 n2 u2 n3 u3. This can be written as dou n1 by dou x into displacement u1, dou n2 by dx displacement u2, similarly dou n3 by dx, and this is u3. This is equation number 3. Okay, similarly the normal strain in y direction, epsilon y equals to dou v by dou y. Similarly dn1 by dy into displacement v1, dou n2 by dou y displacement v2, dou n3 by dou y displacement v3. This is equation number 4. Now we have to calculate shear strain. The shear strain in xy plane. Here we are considering both the planes for shear. That can be expressed as dou xy, that is dou u by dou y and dou v by dou x. Again we have to differentiate these two with respect to x and y. First with respect to y, that is u with respect to y, dou n1 by dou y, dou n2 by dou y, here it is u1, here it is u2, dou n3 by dou y u3. Similarly dou n1 dou x v1, dou n2 by dou x v2, dou n3 by dou x v3. This is equation number 5. Okay, these three equations, strain in x direction, strain in y direction, and shear strain in xy plane, we have to write the same, these three equations in matrix form. That is writing the equations in matrix form. See, here we have three equations, epsilon x, epsilon y, and tau gamma xy. Okay, so here I will write, first is related to strain in x direction, so that is dou n1 by dou x. The second will be 0 because here will be, we have v. Okay, this is for u and this is for v. Similarly n2 by dou x, and this is 0, n3 by dou x, and this is 0. Second one is for v, so it is 0, dou n1 by dou y 0, dou n2 by dou y 0, dou n3 by dou y. Okay, now we have to write this one, shear stress equation here, dou n1 by dou y, dou n1 by dou x, dou n2 by dou y, dou n2 by dou x, dou n3 by dou y, dou n3 by dou x. Here I will write u1, v1, u2, v2, u3, v3. Okay, like this, where n1, n2 and n3 are the shape functions. Okay, and u1, u2, u3, v1, v2, v3 are the constant values. We have to find those values. Okay, so that is say function n1 is 1 by 2a alpha 1 beta 1 x plus gamma 1 y. Similarly n2 1 by 2a alpha 2 beta 2 gamma 2 y. n3 1 by 2a alpha 3 beta 3, here we have to write x, sorry, and this is gamma 3. Okay, now we have to find dou n1 by x, dou n1 by y, dou n2 by x, dou n2 by y, dou n3 by x, dou n3 by y. So now dou n1 by dou x we have to do. Here we have only one x component and this is constant outside. Here is this is the area of the that constant triangle, constant strain triangle. So we'll get 1 by 2a into beta 1. Okay, similarly dou n2 by dou x will get 1 by 2a beta 2. Similarly dou n3 by dou x will get beta 3 by 2a. Similarly this one, second one, n1 by dou y with respect to y. Now here we have only y component, 1 by 2a gamma 1 into dou y is equals to 1 by 2a gamma 2 n3 by dou y, that is 1 by 2a gamma 3. Now we have to substitute these equations, these values in this equation. Okay, for example here we have dou n1 by dou x. What is the value of dou n1 by dou x? That is 1 by 2a beta 1. Like this we have to substitute all these values in this matrix. Okay, from the above equation substitute the above values. Equation number 6, we call this equation as 6. Okay, so this one as it is, strain values x epsilon y gamma xy. Here I will take 1 by 2a as common because everywhere we have 2a 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 2a. Okay, first one beta 1 and next here we have 0, that is 0. Next dou n2 by dou x, dou n2 by dou x is b2, similarly 0 and this will be b3. Here 0 gamma 1 0 gamma 2 0 0 gamma 3. Here dou n1 by dou y, dou n1 by dou y is gamma 1 and this is dou n1 by dou x is beta 1. Similarly gamma 2 beta 2 gamma 3 beta 3. And here we have again u1 v1 u2 v2 u3 v3. Okay, sorry, yes. Gamma 1 beta 1 gamma 2 beta 2 gamma 3 beta 3. Now the same equation can be written as, from the above equation can be written as, see this one is strain, okay, that is epsilon, and this is b, the same entire matrix is b, and this is delta, that is displacement. Okay, that is here the matrix b, this one, that is nothing but strain, displacement, relationship matrix for CST, that is constant strain triangle, that is B equals to 1 by 2a beta 1 0 beta 2 0 beta 3 0 0 gamma 1 0 gamma 2 0 gamma 3 gamma 1 beta 1 gamma 2 beta 2 gamma 3 beta 3. Okay, and where beta 1 beta 2 beta 3, the values are, that is coordinate values are y2 minus y3, y3 minus y1, y1 minus y2, and similarly gamma 1 gamma 2 gamma 3, this is x3 minus x2, x1 minus x3, x2 minus x1. These are all coordinate values, and this delta indicates nodal displacement vector, and this is strain displacement relationship matrix for CST, and this is the strain. I hope you understood. Okay, thank you.